So, hello student. So today we are going to discuss a new kind of stochastic process. So now recall that so far whatever we learn, recall that so far whatever we learn, say Bernoulli process, and Poisson process. Okay, so they are memoryless, right? Memoryless, right? So what does that mean? That means that that is future of the process does not depends does not depend upon the past, right? 1 minute. So future of the process does not depend on the past, but there might be some cases where future does depend on the past, right? For example, suppose uh, suppose that the daily stock price, so on day one, so I'm assuming that it start from zero somewhere or something. On day one the stock price was something, and then it can go either up and or go below, and then on up or below, something like that, right? Okay, so so this type of process where future depends on the past value, right? So if you know the values here, then it can either go up or down, okay, with some probability, right? So this type of process are no longer neither Bernoulli or a Poisson process, right? So you need to describe this by a different method, right? So this type of process do exist in the nature, and so one of such example is called a simple random walk. So let me tell you what is that. So uh, simple random walk. Okay. So what does that mean? That means okay. So first tell me geometrically, and then I will define it mathematically. So if I take for example projection of these points, these values on say integers. So what happens? So you have somewhere zero, and then either you can go one unit right side, or you can go one unit left side. So at each point you have either going these or these or these, or going these like this, right? So your possibilities are either 1 2 3, you start from 0, or maybe -1 -2 -3, okay, and so on. So this is kind of a one-dimensional walk on the integers. Okay, so this is line of integers. Okay, so that's why this kind of process is called a simple random walk, right? Now, how to define mathematically? So mathematically, so now let me define it. So definition. So let x1, x2, x3 be a sequence of IIDs. Okay. So I'm choosing IID. So and with say with uh, probability mass function PMF is so they're taking two values. So these exercises are taking two values only, either one step in right side plus one or one step left side minus one. So with probability that xi is taking value 1 and or probability that xi is taking value minus 1, both are same and is half. Okay, so these xi's are obviously, you can understand, these are IIDs and it has equal probability to take either this and this actually. Okay, yeah, and then you define define y, say yn equal to summation xi I equal to 1 to n. Okay, for I equal to 1 to and y0 you define by 0. So you start with 0 and then it is the sum of this is xi random variables. Okay, then this sequence, then the sequence y0, y1, y2 dot is called a one dimensional symmetric simple random walk. Okay, so I already described why it is called random walk, because this is kind of if you take projection, it's kind of okay. So you have y0 equal to 0 and then y1 depend on the value of x1. So x1 is 1, then it can be 1, then y2 may be 1, then y3 may be 1, and then y4 maybe x4 may be minus 1. So it becomes this, and it can be again these, and then again these and these and these and then these it's like that. Okay, so so it's random because you can, it depends on the value of xi. So xi is taking plus 1 or minus 1 randomly with probability half. Okay, why it is called one dimensional? Because you see that the projection on the image, projection on the integers is kind of one dimensional thing, right? Okay, and this is is the graph. So when you have a map, so this is a time. So like time 1, time 2, time 3, okay, so on. So it's actually one dimension. This is one dimensional, right? And why it is called symmetric? So by symmetric I mean that probability is half. So what does that mean? That means at every point, whenever it is here, so it can go either 1 plus 1 or go minus 1. So it can go to, it has two possibilities. So at any point, any integer, say n, it can go either the integer n plus 1 or it can go either the integer n minus 1 with the same probabilities. That's why it's called symmetric. So in general it may not be symmetric, it can have a different probability of going into different points. Okay, so so this is an example of scheduled random walk, and you may have higher dimension, for example. So note that in one dimension, so there are two neighbors, right? Two neighbors. Okay. But in, say, in two dimension, it has four neighbors, four neighbors, and so on. In three dimension, it has six neighbors. Like two dimension, you can think this kind of a lattice. So if you know value somewhere here, it can go to either this point or these points or these points or these points. Okay. So similarly, in three dimension it can go to three points. Okay. So these are examples of random. I mean, so this is called random walk. I will give an example, obviously, and then maybe you can define some of the properties here. Okay. So so maybe so let me tell you. So what happened? For example, if you want to know that say daily stock price, for example. Okay, so I see when I am taking plus one plus one plus one, so maximum it can go to this line, right? The question is that in the long run, whether you are going to meet this line or this line. So the answer is that no, actually. Okay, so for example, if you go to these, 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 this, like this. So in the long run, what happened? So this is one of the question I asked in the beginning of this stochastic process, that long-term average, what happened? So so one can ask this type of question: long run, how it is behaved? So so long-term average. So what happened to long-term? Okay, okay. So one can easily find out. So so let me find out. So I will use something called central limit theorem. Central limit theorem. Okay. So what the central limit theorem tells you? So now if you check that this xi is this random variable xi is what is the expectation of this random variable xi? So this expectation is 1 into half plus minus 1 into half. So this is 0, and the variance of xi is what? So variance is expectation of xi square minus expectation of xi whole square, right? So this is 0. So this portion is 0. This portion is what? This portion is uh, 1 square into half plus minus 1 square into half, right? So this is 1. So this this expectation is 1 and variance is also expectation is 0, variance is 1. So you can talk about the expectation also, expectation of um, this yn, that simply random walk. So maybe property number 1. So what is the expectation of this? So the expectation will be sum of expectation of I equal to 1 to n, and that because xi is independent, so this will be 0. Okay, and you can say what about the variance? So variance of yn will be sum of variance of xi, because there is no covariance, so this will be n, right? So 1, so yeah, n. Clear? So so what does that mean? So that means that so the standard deviation, so on an average, so here I am talking about, so the average value is 0, right? And the standard deviation is root n, because variance is n. So the graph, say x equal to say root x, this kind of parabola, right? Yes. So in the long term, this value won't go far from this time, right? So for example, with high probability, say 95% something probability, this graph will be in between this parabolic domain. Okay, and there is a theorem that they touch both the parabolic, both these things infinitely often. Okay, so so central limit theorem tells you that um, central limit theorem tells you that this yn, which is summation of xi equal to 1 to n, and then variance is what? Variance is say standard deviation is root n, so we can say that yn by root n. This is actually normally distributed with 0 1, okay, as n tends to infinity. Okay, so what does that mean? That means this yn is some constant time approximately equal to yeah, so this limit value is this, so approximately equal to constant time into time. Okay, so so theoretically that means, sorry, yeah, geometry, that means that the value will be almost most of the times inside this car. It will go maybe sometimes, but on an average it cannot go very far from this parabolic region. Okay, in fact, there is a theorem that if you, so on say on integers, on a line of integers, uh, so z, okay, and if you want to find out what is expectation of mod of yn, uh, rather, yeah, so um, yeah, so yeah, mod of yn, um, so yn is 0, and you can find out what about the properties. Okay, so 1 2 3 4, so same thing. So this is random walk on integers, and this graph is same, right? So now question is that how do I mathematically formulate this kind of idea, like okay, so maybe, so one example I should give here. So this is very important example. This is called um, game of gambling. So I will describe this later, but let me just tell this. So gamblers ruin problem. Okay, so a gambler is actually playing some gambling game, and just suppose he has some money, say a amount of money, and every time he is playing a game, either he will win, say, one amount of money, or he will lose one amount of money, okay, minus one, okay, either win or loss. Or maybe I am performing a coin toss, so tossing coin, so whenever head comes he win, whenever tails come he lose, right? The question is that if you start with a money, whether you will reach something, say b amount of money or not. So he will stop playing, either he will reach b amount of money or he will reach zero amount of money. Okay, and now question is that what happened, so when he will going to stop. So it depends on the probability, the probability of getting one. Say here I am tossing a coin, so the probability half, okay, but it can be a different game also, the probability can be different also, okay. So in this case, this kind of problem is nothing but example of simple random walk, okay. So I will come to this problem, and I will solve completely using something called Markov chain in maybe next class, okay. Clear? So this is the overall idea of stochastic process, which the present state depends on the past state, because you see every time, if, say for example, whenever I am here, the value will be either this or this, right? So this next value is depends on the current value, right? So this type of process is called actually Markov chain. So now let me mathematically define what is that, but I need to describe some of the terms there. So let me start with this called discrete time Markov chains. Okay. So yeah, so before going to give this mathematical definition, so let me just tell these things. So suppose, so let S be the set of all possible outcomes of this random variable exercise. Okay, so this exercise random variable, which is IITs, I already defined it. Okay. Um, okay, so and I am assuming also, so this S is called the state space of states. Okay, and element element elements of S are called states. Okay, so now I will for the time being, for this analysis I will assume that my S is finite. So S is some finite set. So 1 2 3 dot, 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 m. It's a finite set. So what does that mean? That means that is this exercise are taking finite values, um, taking only, yeah. So not only, sorry, not exercise, so this summation exercise. So yi, this yns, yi's, which is summation I equal to 1 to n. This is taking these finite values. Okay, so now or rather, maybe I can just set xi. I don't want yi here. Okay, xi is enough for me. So finite values. Okay, for the time being. So I'm assuming this, and then we define something called Pij. Pij is the probability that your xn plus 1 is taking the value j, given that xn taking the value I for some I and j belongs to S, and n is some natural number. Okay, for some n. Okay, this is my symbol. Pij is the probability that your xn is taking value I, and the next state next random variable xn plus 1 taking value j. So that means you are going from the I state to the j state. So that is you're going from I state to j state. Okay. So with this property, so let me define what is a Markov chain definition. So a Markov chain is a sequence x1 x2 of um, random variables the general definition. Okay, that take values in S, and the probability that xn plus 1 will be j given all the previous probabilities like x of n equal to I, and then xn plus n minus 1 equal to something in minus 1, and so on, x1 equal to I1, and then x0 equal to say I0, whatever you know, all those things. You can start with x0 here also. Okay, this probability is only depends on the last one, the init position, which is I. This is nothing but probability xn plus 1 equal to j, uh, given that x equal to I. Okay, so that is this pij. Okay, so what I'm saying that the probability of the future state depends on only on the current state. So what is the meaning? So that is the probability law of the next state. So whatever in next state, xn plus 1 depends on the past only through the value of the present state xn as xn. Okay, so there is, xn does have the value does depend on the past, but is only depend on the last one, the last state. Okay, so for example, the simple random walk is one of the example here, right? So you have whatever we discuss symmetry simple random walk. So you go here and then go there, and then now if you want to go here or here, it does not depend on this value, right? It depends only these values. You can go here or here. Okay, similarly if you are here, so you can go up or head down, that also depend on this place, not this place. Okay, so this is an example of Markov chain. Okay, so and I mean, why this Markov chain? So for this simple symmetric random random walk, what happened? That probability that x n plus 1 equal to something, say j, uh, this whatever this, so given whatever xn, this is whatever value I n minus 1 equals some I minus whatever dot and so on, whatever. So this is only depend on this is half. Okay, and this is if uh, okay, so from here to here you're going half. If what happened, so you are setting at I position, you're going to j position, and this is only possible if this I position. Okay, so if uh, j equal to, so j equal to I plus 1, or j equal to I minus 1, right? So that means whenever you are on I stage, so either you're going to j, you're going up 1 or down 1, and that is only possible this thing, right? So it depends on only this I position or 0. So it can be this or this, or 0 otherwise. So what does that mean? That means for simple random walk, if you have state 1 and you cannot go to state 3, 0. Okay, so you can either go to state 2 or state 0. This is the simple random walk. Okay, with probability half. Here also you have probability half, so I'm assuming that symmetrical. Okay, and probability from 1 to 0, 1 to 3 is 0 actually. You can't go there. In transition probability. Okay, so now this has a nice name. So uh, these PIJs are called the transition probabilities. Okay, transition probabilities and 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 um, and one can define a matrix like this, like P11, P12 dot dot, say P1n. There are many states, and then dot dot PM1 dot PMM. Okay, a matrix of this form. So you can write down something, say a matrix E, whatever. So this is my, I'm giving a name. So which is called the transition probability matrix, probability matrix of the Markov chain. Okay, and we will show that this matrix is it is actually contains all the information of the Markov chain. So if you know the matrix, you know everything on the Markov chain. That you can, I will show you. Okay, so so now also note that when you add this row wise, what happens? Every row, if we add every row, so what does that mean? That means you are standing at state 1 and you are adding the probabilities that can go to it can remain state 1 or go to state 2 or go state 3 or state 4, state m. There are n many states. So the summation, note that the summation over j, Pij, and j equal to say 1 to m. There are many states, right? So the sum is always 1, because whenever you are in the state I and you can go to there are many states. Okay, and total probability is 1, so either you can go to state number 1 or 2 or dot, 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 or m, right, some m minus 1, so you can go to any state, and the total sum of total probability is 1. So this is true for all j equal to 1 to m. Okay, so what does that mean? That means if you add this row wise, the probability is always 1. Clear? Okay, so this kind of graph is called a transition probability graph. So what is that? So transition probability graph, transition probability graph. So what is that? So you have you have state S 1 2 dot, dot m. So you write down the vertex of the graph by the state, say 1 2 3 and some dot dot something like m, and then you can either stay here. This probability is p11, you can go there. So this is p12, you can come here. So this is P21, and then go there P23. If there is no these PIs are probability, it can be it cannot be negative, it can be 0 or this. If there is no age from say 1 to 3, then P13 equal to say 0. Okay. If there is a age, then it has a positive probability. Okay, and so on. So this kind of graph is called the transition probability graph. Now let me give an example properly. So uh, this. Okay, okay, so example. Um, so a student of this MA203 course uh, course uh, can have two states, either every week. So either up to date, up to date every week, uh, or maybe fallen behind. Okay, so those are not learning from my videos, maybe fallen behind, and those are doing every day, so they may be up to date. Okay, so every week. So now uh, if uh, C or E, whatever, is up to date in a given week, the probability, the probability that C will be up to date uh, in the mm, in the next week is 0.8, and fallen behind fallen behind uh, in the next week is 0.2, right? So he is up to date, then he can have two possibilities next week, either up to date or fallen behind. Okay, now again, if C or E is fallen behind in the current week, fallen behind in the current week, some current week, the probability that theory will be up to date in the next week is 0.4. Okay, so if already fallen behind, so next week you will up to date with probability 0.4 and fallen behind with probability 0.6. Okay, now can you so and obviously I am depend, so assuming that this fallen bin up to date is independent to it depends whether what happened to the current week, not the previous and previous week. Okay, now can you explain this problem using Markov chain, right? So now in Markov chain, what you can do, so so you have, so let us now uh, let us introduce, so that states, so here you have two states, right? States one, which is, so maybe up to date, which is up to date state, and states two, which is fallen behind. Okay, so then what happened? Then it is clear that 1 1 will up to date, if it's up to date in 1 week, and then it will be again up to date in the next week, is nothing but 0.8. Okay, but 1 2, which is nothing but 0.2. Okay, and then probability 2 1, if fallen behind, then it will up to get 0.4, and 2 2 is 0.6. Okay, so the so this is the transition probabilities, and then transition probability matrix. Transition probability matrix is what? So this is kind of this 0.8, 0.2, 0.4, 0.6. Okay. Now you can also associate graph also, like 1, 2, then it can come here. This is with 0.8 probability, from here to here, 0.2, there to there, 0.6, here to here. So this is the so this is the transition probability graph. Okay, so by this you can explain this whole problem. Clear? Okay, so maybe I will stop this new learning today here. But before I end this today's lecture, I am going to give a quiz. So this quiz, okay, and this quiz is based on my previous lectures, lecture number 33, 34, 35, those lectures. Okay, so you need to those who did not watch, and maybe those who are not maybe who did not learn, I advise you to go back and watch the videos and try to understand and then solve the problem. Okay, see, in your last solution, most of the people have solved send me the wrong solution. Okay, and I understand you guys just copy paste your solution, it is clear. And whenever I am telling you that do something at your homework, so that is actually I'm asking you to solve by your own. Clear? And you solve this problem and send me the solution by say 28 04 midnight. Okay, till this midnight. Send me the solution by midnight. Okay, now what is the problem? So problem is, so a packet consisting of a string of n symbols, okay, and that is transmitted. So this n symbol is transmitted over a noisy channel. Each symbol each symbol has probability p, which is 0.0001, okay, of being transmitted in error. Okay, so the error of transmission is 0.0001, okay, and that is independent of of other symbols. So if there is a error in one symbol, that does not depends or does not have an impact on the error of other symbol, right? Now question is that, okay, so there is a problem here. Okay, the question is that how small should n be in order for the probability of incorrect transmission to be less than 0.001. Okay, so the symbol, what should be the highest maximum value of n possible for which the error will be less than this. Okay, so what does that mean? If n is bigger than that number, then the error will be more than this number. Okay, this is the question. So I hope you understood it, and you try to watch the videos and try to understand and solve this problem. Okay, so with this I will stop today's lecture. Bye, goodbye.